So in this video, we're going to cover the second half of chapter 26, and then we'll cover all of chapter 27. And I think this video will actually be smaller than chapter 26 video was. Sorry, that was 50 minutes. This hypothesis test is totally new to us, so it does take a bit of time to get through it as we're introducing it. So chapter 26, what we did was we covered z-tests. Whoops. So if we look on Canvas, you'll find a cheat sheet similar to the one I had for homework or exam 2. This cheat sheet, you're not going to be allowed to use it on the final. The final will be closed book. You'll be given a formula sheet with all the formulas on it, but that's it. So once we get through chapter 26, 27, and 28, and you get exam 5 done, quiz 5 done, you can start preparing for the final. And I'll have more info for that here pretty soon. But yeah, this cheat sheet summarizes everything we're going to cover in these 3 chapters. So we covered the z-test. How you know you're going to be doing a z-test is it will ask, does the sample average percent match what was given or expected? So we looked at light bulbs. Was the life expectancy actually 500 or did it average lower than that? And we used the z-test on sample sizes bigger than or equal to 30. And then we just went through these 4 steps to do it. What we're going to talk about now is a t-test. And a t-test, it's the same thing as a z-test, except you use a t-test if your sample size is smaller than 30. And then these are the steps we take, and you'll notice they're basically the same steps as a z-test, except you'll see in here it says shade T and SD plus right there. So that's what we're going to talk about, is what those things are. Okay, so this guy right here, who went under the pen name Student, he came up with the t-distribution, and you use a t-distribution if your sample size is less than 30. So if you're sampling 15 data values instead of like 50, you can't sample 50 people or whatever. This is when you use a t-distribution. And a t-distribution, it's similar to the normal curve, except let's jump over a couple times. You can't use the normal curve for small sample sizes because it's so small. The central limit theorem that guarantees it will follow the normal curve, it doesn't work on it because it's not a large sample. So the t-distribution looks like this. There's more area in the tails here, and it changes based off of the sample size. If your sample size is 3, it's going to look something like this. If your sample size is 20, it's going to look something like this. So it changes based off of your sample size. Because we're working with small sample size, we run into a problem where our standard deviation is actually going to end up being smaller than this real standard deviation, the standard deviation for the full population. So we use what's called the SD plus. And this slide explains it, but this slide does too, so I'm just skipping that slide. The standard deviation plus, it inflates the standard deviation just a little bit so that it's bigger, so it matches the true population better. So this is when we're using a t-distribution or a t-test. We use it because the sample size is smaller than 30. If you've got the sample size that's smaller than 30, you're going to use the SD plus. And the way I remember that is plus and T are the same symbol. So we've got this standard deviation plus. It's calculated with that formula right there. So we have a sample size of 10. That's smaller than 30. So our sample size of 10 exam scores has a standard deviation of 14.5. We need to inflate that just a little bit by doing the square root of the number of measurements divided by the number of measurements minus 1. 10 minus 1 is 9 times 14.5. So the square root of 10 divided by 9. And then multiply that by 14.5. So it's inflated just a little bit, it becomes 15.3. And then when you calculate the SE, so you can work with the standard error, you use the standard deviation plus instead of the standard deviation. So we'll use that quite a bit more here in a minute. The other thing we need to know about the standard, or about t-curves, is degrees of freedom, or DF. The degrees of freedom is what determines the shape or the height of the student curve, the t-curve, because sometimes it can be really tall. Woo, that's funny looking. Sometimes it can be quite short, like this dashed curve right there. And the degrees of freedom is simply the number of measurements minus 1. So if there's 10 measurements, the degrees of freedom is 9. And when you go to calculate the area under the curve, instead of using shade norm, we're going to use shade T now, where it's still the lower bound and upper bound, but then instead of 0 and 1, we use the degrees of freedom to find that area under the curve. So we'll do that here in a minute as well. Oh, yep, right here. So it says find the area under a t-curve with degrees of freedom of 8 to the right of 1.9. So it's saying we've got our t-curve. We're looking to the right of 1.9. Sorry, I don't know why that looks so bad. Let's try that again. Okay. To the right of 1.9. So we're going to do shade T instead of shade norm because it says t-curve. To the right of 1.9. So 1.9 to 10. Let's just make sure. We're using a different curve, so we want to make sure 10 is still a big standard deviation. And it should be, okay, we're not too goodness of yet. Yes, 10. Okay, so 1.9 to 10. So again, if it just goes off to the right, you're still using just a big number, which is 10. And then our degrees of freedom is 8. And you don't have to subtract 1 because it already told you the degrees of freedom, not the sample size. So then we just type that into our calculator. So we go to calculator. And you get there the same way you get to a shade norm. You go second, vars, arrow over to draw, and it's the second option instead of the first. And then your lower bound, you'll tell it it's 1.9. Upper bound, you'll say is 10. And then our degrees of freedom is 8. And you can choose a color again. Okay, so here's my t-curve. And it works just the same as a shade norm. Shade T gives you the area just like the shade norm. Looks like our area is 4.7%. Okay, so we can do that for this one. Find the area under the t-curve with degrees of freedom of 20 to the left of negative 1.36. So here's negative 1.36. We're going to the left. So that means we're going to go from negative 10 to negative 1.36. Oops. I hate this calculator. So we're going to go second vars, arrow over to draw, choose option 2. Nope, that's chi-squared. -10. Negative, what was the number? 1.26, negative 1.36. And then our degrees of freedom was 20. Choose whatever color you want. And well, it drew it, but it still has the old t distribution in there. Okay, this orange area is, my calculator's thinking, 9.4%. So that's how you use shade T. Let's not worry about that one. Okay, here's the steps for t-tests. You use if the sample size is less than or equal to 30, and we're just going to do less than 30. If it's equal to 30, use the normal shade norm. And then it's the same steps. You write your null and alternative. The null is what it's supposed to be, or it's equal to what it should be. The alternative is it's less than or it's greater than what it should be. You go through and find the test statistic. This time, SE is going to be equal to the SD plus divided by the square root of the number of draws. And then T is the same formula as Z. So you'll find T score instead of Z score, but it's the same thing. It's what you want minus the expected value over the standard error. And then you find your p-value usually using shade T. And then you write your conclusions. If it's greater than 5%, or sorry, if it's less than 5%, you accept, I'm struggling with reading this. Okay, if the p-value is smaller than 5%, you fail to accept the null, or you reject the null. If it's greater than 5%, you accept the null, or fail to reject the null. Okay. Let's do a problem. So a major manufacturer wants to test a new engine to determine whether it meets new air pollution standards. The average emission of all engines of this type must be no more than 20 parts per million of carbon. 10 engines are manufactured for testing purposes, and the average is found to be 24.1. Standard deviation is 3. Okay, so we know 3 things. The average is 24.1. Standard deviation is 3. And our sample size is 10, which is less than 30. So we get to use T. Assuming that the engines are like a simple random sample from a very large population and that the emissions follow the normal curve, is there evidence that this type of engine fails to meet the pollution standard? So we want to know, is 24 too big compared to 20? So our null is the average emission is 20 parts per million. The alternative is it's not. And more than it's not, it's greater than. Because if it was less than, it wouldn't be a big deal. It just has to be no more than 20. So the average is greater than 20 parts per million. Oh, we just wrote the hypothesis on the previous page. Okay, our test statistic. So let's look at our cheat sheet so we can see our steps. we write our null and alternative, and then we need to calculate our standard deviation plus. So our SD plus is going to be equal to the square root of the number of draws, or the sample size, over sample size minus 1 times the standard deviation. .16, so I'm going to say 3.2. Okay, we need expected value and standard error to calculate our test statistic. That means the t-score. So expected value is what it should be, 20. It says right here, average of the box, or what we expect it to be. The standard error is the standard deviation plus divided by the square root of the number of draws. And this is averages. I should specify that. 3.2 divided by the square root of 10. It's going to be about 1. Yep, 1.01. Can you hear my dog licking or drinking now? I need to move out of the front room. That's why you can hear her so well on this one. Okay, T is going to be equal to what we got, that 24.1, minus what we expected to get, divided by the SE plus. Good criminy, she's still drinking. Okay, our degrees of freedom is going to be 10 minus 1. So our p-value is calculated by doing shade T. And we're looking for the chance of getting 24.1 or more extreme. So 24.1 is bigger than what we expected. So it's going to be 24.1 or more extreme means shading to the right. So for 24.1, we got, oh, I didn't calculate that. I got distracted by the dog. 4.1 divided by 1.01, 4.06, or more extreme, with degrees of freedom of 9. Second vars, arrow over to draw, down to shade T, 4.06, 10, 9. And our p-value is, very slow calculator, 0.14%. Okay, that means we reject the null. Because it's less than 5%, that's our acceptance value. If you look at our cheat sheet here, we see that. So we're going to write, there is evidence to conclude the average is greater than, because that's what we got. 24.1 is greater than 20. Okay, and that's our t-test. It's basically the same as a z-test, except you're using shade T and SD plus. So let's look at another one. We've got 2 more examples. Yep, 2 more examples of this type. Okay, a vitamin pill is advertised as containing on average 500 milligrams. So it should be 500 milligrams of vitamin C. A consumer protection organization wants to make sure that the true average isn't much different than 500 milligrams. A random sample of 7 pills. So we've got 7 pills. So we know we're going to be using T instead of Z because it's smaller than 30. For actual vitamin C content, the following amounts are observed. The pill's vitamin T or vitamin C amount have approximately a normal distribution. Is there a problem with the amount? So let's quickly calculate the average for this. So we're going to go into 1-bar stats. So start by typing this into your list by going to Stat, Edit, and then Stat, Calc, 1-bar stats. It looks like the average for this is 507.4, and the standard deviation for this is 10.9. So I calculated those because they weren't given to us. Most of the time they will be given to you. But if they're not, you can just quickly use 1-bar stats to get them calculated. Okay, so it's greater than what we expected it to be. So our null is going to be average is 500 milligrams. Our alternative is that it's not, and more than just it's not, it's greater than, because we got a number that's greater than. So average is greater than 500 milligrams. So let's test that. Oh, again, I wrote the hypotheses on the other page. Let's calculate our SD plus. So we had 7 samples. So we're going to do the square root of 7 over 6 times our standard deviation of 10.9. To get 11.8. Notice it's bigger than our actual standard deviation. That's how it should always be. And then we're going to calculate our expected value and our standard error so that we can get T. So the expected value is always the number it gives you. We're expecting 500. Standard error is the standard deviation plus divided by the square root of the number of draws. .5. Okay, we got 507.4. We expected to get 500. The standard error of 4.5. So 1.6 standard errors from the average. So we can use that number. Remember, we're always looking more extreme than that. So since it's positive, we're looking at 1.6 or more extreme when we do shade T. If it was negative, you would have shaded to the left. So you'd go to -10 instead of +10. So we get degrees of freedom is 7 minus 1, or 6. So p-value is going to be shade T. Oops. 1.6 to a big number, so 10, with degrees of freedom of 6. And we can type that into our calculator. Nope, it didn't clear it. I don't remember. What did I do to clear it? That should do it, right? That still didn't do it. Let me try this one more time, and if it doesn't work, I'm going... to just use my normal calculator. Yep, okay, I'm just going to type it into the normal calculator. I'll just show you really quick, just in case you're still wondering. So you go second, vars, arrow over to draw, choose shade T, and then lower bound is 1.6, upper is 10, degrees of freedom, and then you can just graph it, and yours should show you what it is. I'm not loving this calculator, so let me do it on my real calculator. Looks like 8%. Okay, that's greater than 5%, so we accept the null. Well, we never actually accept the null. We fail to reject the null. Which means it looks like on average, it is really what it's supposed to be. 507 isn't different enough from 500 that it's concerning to us. So it appears that the average is 500 milligrams. Okay, this one, I'm not going to do this one because it's just the same thing. If you want to do it, you can. What you should end up with is a t-score of negative 2.2. And then you should do shade T negative 10, negative 2.2, 2 degrees of freedom should be 15, and then you'll end up getting a really small p-value, and you'll reject the null, or fail to accept the null. Okay, so we've covered 2 types of hypothesis tests so far. We've got our z-test, our t-test, and now we're going to talk about our 2-sample z-test. You use a 2-sample z-test if you're comparing 2 samples. So we'll see a couple examples of that as we go through this. Okay, do people see billboards? We've got this question right here. And what we want to know is, are billboards actually effective? So a billboard company takes a simple random sample of 500 Salt Lake City residents and finds that only 26 knew that Calvin Coolidge was the 30th president. They then put up several yellow billboards that say Calvin Coolidge was the 30th president. After a few weeks, they take an independent simple random sample of 500 residents, and this time 158 answer correctly. So is this evidence that people see the billboards, that billboards are effective? So in our first sample, 26 of the 500 knew who the 30th, or that he was the 30th president. That is 5.2%. After a few weeks of the billboard being up, they did the sample again and found 158 out of 500, or 31.6% knew. So we want to know, is this a significant change? And it looks like it is. I mean, that's like a 25% difference. So we want to know, is that a big enough difference that we can say billboards are effective? You should use them for advertising. Okay, our hypothesis for a 2 sample z-test, the null is that the samples are the same. The alternative is the second sample is different from the first sample. So our null is going to be the samples are the same, or billboards are not effective. The alternative is second sample is bigger than first sample. And we know it is, we just need to make sure it's significantly bigger, that 25% difference is big enough that we can really say it's bigger. Or, in other words, billboards are effective. And you don't have to write both of these, I'm just showing you 2 different options. Okay, the expected difference, if the samples are the same, we'd expect to see a 0% difference between the 2 samples. That's always going to be 0. So if we look here, the expected value difference is always 0. And then the observed difference is the difference from the second sample minus the first sample. So 31.6 minus 51.2. Sorry, 5.2. .4%. Okay, because we have 2 samples, it means we have 2 different standard errors, but we need just 1 standard error in order to calculate our z-score, because you do the observed minus the expected divided by the standard error. So we need to use this formula to calculate the standard error. So it's the square root of the standard error for A squared plus the standard error for B squared, or sample, the first sample and the second sample. So in our first sample, we observed 5.2%. So 5.2% were 1s, and then the rest, 100% minus 5.2, were 0s. Meaning the standard deviation of that box is going to be the square root of 5.2 times 94.8, except we have to move the decimal twice. So it's actually going to be the square root of 0.052 times 0.948. Okay, I know this is a lot of new stuff. If you need to take a break, just step aside for a minute, pause the video, and then come back to this. We're going to do this a couple times, so you'll get the hang of it between this and the homework. So I know, I really do know this is a lot. Okay, This standard deviation of the box, that formula I just used, came from this percent of ones times the percent of zeros. We did that in the previous stuff as well, so hopefully it doesn't look unfamiliar to you. Standard error percent is equal to the standard deviation of the box divided by the square root of the number of draws times 100%. Or essentially 1.1%, it's 0.98%. Okay, so we've got our standard error for sample A. Next, we need to find our standard error for sample B. So we got, what was it? 31.6%. And again, I got that by doing 158 divided by 500. So the standard deviation of the box, this time our box has 31.6% of people did know. So then the other part of 100%, 100 minus 31.6, so 68.4% did not know. Oh, I lied to you when I said this was going to be less than 50 minutes. Sorry, this is going to be a long video too. I don't know if I said that actually. I said it in my head. I thought this was going to be a shorter video. It's not. .46. Okay, so the standard error percent is 0.46 divided by the square root of the number of people times 100%. You don't type a percent in your calculator. I just put that there to remind me I'm changing it into a percent. Whoops. Square root of 500. Okay, so it's 2.1%. Okay, we're going to do the square root of the standard error for A squared plus the standard error for B squared. And that probably looks familiar to you because it is the Pythagorean theorem. So we're going to do the square root of 0.98 squared plus 2. You know what? I did 2 decimal places on that first one, so let's do 2 on this. 2.06 squared. Don't forget the squared on those. Let's type it in over here. Okay, 2.28 is our standard error. And this is called the standard error difference. What was it? 2.28? Because it's the two samples combined. So it's the difference between the two samples. That's what we're looking at. So this is our standard error. So we can now calculate the test statistic. It's Z again. Z is the observed difference. What was it? 26.4. Yes, 26.4 minus the expected value difference is always 0% difference. Over the SE, we got 2.28. So then we type that into our calculator. Sorry, typing it into my calculator. That is 11.6. Okay, that's a giant z-score. So you can do shade norm if you want to, 11.6 to 10. But you can't use 10 because 11.6 is bigger than 10. So you'd have to do like 100, 0, 1. That's going to give you 0%. 11.6 standard deviations away is very big. So you know, yes, we are going to reject the null or fail to accept the null. There is evidence that billboards make a difference or are effective. Okay, a lot of people struggle with knowing which one they're supposed to do. Do we accept or do we fail to accept? If you get stuck, look back at the cheat sheet here. And it tells us right here, if it's greater than 5%, accept the null. If it's less than 5%, fail to accept the null. Okay, so this was a percent problem. Let's do an average problem. And then I think we'll be up there. Will be another one. I don't want to do that one. Yeah, we're just going to do one more problem, and then I'll give you the answers on the last one if you want to do it. Okay, the National Association of Colleges and Employers conducts surveys of salary offers to new college graduates and publishes the results in Salary Survey. A random sample of 35 liberal arts. Okay, it's bigger than 30, so we're good to go. Graduates shows an average starting salary of that amount. Okay, so for the liberal arts majors, the starting salary is $30,090 with a standard deviation of 1820. For a different, and this sample size is 35. For criminal justice graduates, we have 32 people surveyed. The average starting salary was $27,800 with a standard deviation of 1730. Is this significant evidence that the starting salary of liberal art graduates is higher than criminal justice graduates? There is our null, actually our alternative. So our null is that their starting salaries are no different. The alternative is that liberal arts salaries are higher than criminal justice. And then we need to conduct an appropriate hypothesis test. State your null and alternative, your test statistic, p-value, and conclusions. Okay, the hypothesis is starting salaries are no different. Between the two degrees. The alternative is liberal arts starting salaries is greater than criminal justice. So the observed average that was given to us was 30,090 for liberal arts. That was a half bar. sorry. The dog's gonna go crazy because somebody rang the doorbell. Hey, Juno, come here. Juno. Juno. Stop, okay? I'm trying to teach. You've got to be quiet. Okay, standard deviation we were given is 1820. Nope, you don't need to bark. Not necessary. So our standard error, we can calculate the standard error as, okay, we're in 2 sample z-test. Standard error for average is right there. Standard deviation divided by the square root of the number of draws. And it was 35, right? Yes. Okay, then we've got, oh, we have to calculate that. So this was for liberal arts. This is for criminal justice. The observed is 27,800 with a standard deviation of 1730. So our standard error is 1730 divided by the square root of the number of draws. Okay, the standard error difference is what we need. So we calculate that by doing the square root of the first standard error squared plus the second standard error squared. $433.7. Okay, that's our standard error difference. Let's quickly calculate the observed difference while we're on this page. So we're going to do 30,090 minus 2780 or 800. So this observed difference is 2290. We would expect a difference of 0. There actually is a difference of 2,290. So Z is equal to our observed difference minus our expected difference over our standard error difference. Shoot. What was that? 433.7. Okay, that is another very large standard error, z-score. So we know the p-value is going to be 0% without even having to calculate it. If you want to, you can do shade norm, 5.3 to 10 to 0 to 1, but it's 0%. So we reject the null or fail to accept the null. And we conclude there is evidence that liberal arts degrees have a higher starting salary. Than criminal justice degrees. Whew, okay. Last one, and I'm not going to take the time to do this. I don't feel like it's worth sitting there and watching if you don't need to. I will give you some numbers though, so you can make sure you do this one right if you're going to do it on your own. So if you're doing it on your own, just like pause the video and then look through and see if you got these numbers right. And this is your homework. It is due Friday, May 15th. It would be great if you can get it done by then so you can start preparing for the final. Our final is Friday, May 22nd. I'll have it open Thursday, May 21st through Sunday, May 24th. I think I need to make sure I can do that, but that's the plan. And that final will be on USG's Canvas. Quiz 5 is just you getting onto USG's Canvas and showing me that you